The telescope had been built for one of humanity's grandest ambitions. Its mirrors were meant to peer farther into space than any instrument before it, capturing the faint light of the first galaxies that formed after the birth of the universe. Every hour of its observing schedule was precious, fought over by scientists across the world, each hoping to unlock another mystery of the cosmos. Yet one day, that extraordinary telescope was asked to set all of that aside for something far closer to home. Instead of looking billions of years into the past, it would have to answer a much more immediate question. Was a rock roughly the size of a 10-story building on a collision course with Earth? Not once, but twice, separated by an entire year, that question would return. And the story of asteroid 2024 YR4 would become one of the most remarkable real-world tests of humanity's planetary defense system. A story whose ending looked nothing like anyone expected when it first began. It all started on December 27, 2024. High above Rio Hurtado, Chile, a network of automated telescopes quietly scanned the night sky, doing exactly what it had been designed to do every single evening. The system was known as ATLAS, the Asteroid Terrestrial Impact Last Alert System. And unlike giant observatories searching for distant galaxies, its job was far more practical. It searched for dangerous objects wandering through Earth's cosmic neighborhood. That mission existed because of a painful lesson learned more than a decade earlier. In 2013, without warning, a relatively small asteroid exploded high above Chelyabinsk, Russia. The blast shattered thousands of windows across the city, and the shockwave injured more than 1,000 people. Nobody had seen it coming. The object had simply appeared, exploded, and disappeared before anyone could react. The asteroid Atlas detected that December night was even larger. At first, it looked like nothing more than a faint moving point of light drifting across the stars. No one had ever cataloged it before. It was a brand new discovery. Astronomers assigned it the name 2024 YR4. Initially, there was little reason to panic. Early calculations suggested that the asteroid carried roughly a 1 in 100 chance of striking Earth on December 22, 2032. Among planetary defense specialists, numbers like that were almost routine. Every month, astronomers discovered hundreds of new near-Earth objects. Early impact probabilities often looked unsettling because they were based on only a handful of observations. Almost without exception, additional measurements quickly pushed those probabilities down to zero. Everyone expected 2024 YR4 to follow the same pattern. Instead, it did the opposite. As January 2025 unfolded and more telescopes measured the asteroid's position, the odds refused to fall. They climbed. By late January, the impact probability had risen to 1.2%. By the middle of February, it had reached 2.1%. Then, on February 18, 2025, NASA's monitoring systems briefly displayed something planetary defense experts had never seen before. The probability reached 3.1%. For an asteroid estimated to be large enough to flatten a city if it struck directly, it became the highest recorded impact probability ever assigned to an object of its size. To help people understand risks like these, astronomers use the Torino scale, a ranking system that runs from 0, meaning no concern at all, to 10, meaning a certain global catastrophe. 2024 YR4 climbed to level 3. That number did not mean the world was doomed. Instead, it signaled something much more specific, a close call worthy of serious scientific attention, though still far from a reason for public alarm unless the risk remained for years. Even so, nothing in the history of organized planetary defense had ever reached that level and stayed there. To many observers, the rising percentages seemed terrifying. Surely increasing odds meant the asteroid was becoming more dangerous. In reality, the opposite was happening. The danger itself wasn't growing. The uncertainty was shrinking. Imagine standing in a dark room and throwing a dart toward a wall you can barely see. At first, all you know is the general direction the dart traveled. Its possible landing points form a huge cone spread across the wall, and somewhere within that broad area sits a tiny target labeled Earth. As more observations arrive, it is as though someone slowly turns on the lights. The cone becomes narrower and narrower. If Earth happens to lie near the center of that shrinking cone, instead of near its edge, the calculated odds naturally rise. They continue rising until the uncertainty finally becomes small enough either to include Earth completely, which almost never happens, or to exclude Earth altogether. That was precisely what astronomers were watching unfold. Recognizing how unusual the situation had become, the European Space Agency made a decision almost never seen in modern astronomy. They asked for emergency access to the James Webb Space Telescope. Normally, scientists from around the world spend months, sometimes years, competing for a few precious hours of observing time on Webb. Demand for the telescope is enormous, while available observing hours are extremely limited. However, Webb reserves a tiny amount of emergency observing time, known as director's discretionary time. It exists for situations where waiting through the normal review process would mean missing a critical opportunity entirely. It is used only a handful of times each year. Requesting those hours meant arguing that an asteroid discovered only 7 weeks earlier deserved to move ahead of research proposals that other scientists had spent years preparing. Nobody complained. Everyone understood why it had to happen. Within days, the request was approved, and the telescope originally built to study the birth of the universe turned its attention toward a small wandering rock much closer to home. The reason the James Webb Space Telescope mattered so much came down to something surprisingly simple. Every telescope on Earth, no matter how powerful, faces the same limitation when it observes an asteroid. It sees sunlight reflecting off the object's surface. But reflected sunlight can be deceptive. A small asteroid with a bright reflective surface can appear just as bright as a much larger asteroid covered in dark rock. To a ground-based telescope, both can look almost identical. Webb looked at the problem differently. Instead of measuring reflected sunlight, it measured the asteroid's own heat, the faint infrared radiation it naturally gave off as it traveled through space. That allowed astronomers to determine the asteroid's true size, regardless of whether its surface reflected a great deal of light or almost none at all. That distinction mattered enormously. A rock measuring 40 meters across and one measuring 90 meters across might both fit inside the estimates produced by ground-based telescopes, yet the consequences of an impact from each would be dramatically different. Before anyone could truly understand the level of danger, they first needed to know which one they were dealing with. Even while Webb's emergency observation request was making its way through the approval process, astronomers continued collecting fresh observations from ground-based observatories around the world. Almost immediately, the numbers began changing again. On February 19, 2025, the impact probability dropped from its record-setting value to 1.5%. Only 1 day later, it plunged again, falling to just 0.27%. By the end of February, the possibility of an Earth impact in 2032 had been effectively ruled out. The Torino scale rating slipped back to level 1 before eventually returning all the way to level 0. In the end, Earth had never truly been in serious danger. Those frightening weeks had simply reflected a period when the asteroid's future path remained uncertain enough that a small but genuine chance of disaster still existed somewhere inside the calculations. Even with Earth safely out of harm's way, Webb's observations continued exactly as planned. the mission had changed. Instead of protecting Earth from an immediate threat, astronomers now wanted to answer another important question. They wanted to know whether the James Webb Space Telescope could become a reliable emergency tool for planetary defense whenever future asteroids demanded rapid and precise measurements. In March of 2025, Webb finally turned its mirrors toward 2024 YR4. The answer came back with remarkable precision. The asteroid measured somewhere between 53 and 67 meters across, roughly 174 to 220 feet, about the height of a 15-story building. That single measurement dramatically narrowed the previous estimate, which had ranged from 40 to 90 meters. At the same time, it quietly settled another long-running uncertainty by revealing how reflective the asteroid's surface actually was, something only direct infrared observations could determine with confidence. For most of the world, this was the moment the story ended. The headlines disappeared almost overnight. Once Earth's impact probability dropped to zero, public attention moved elsewhere. But for the scientists still following the asteroid, the most important chapter was only beginning. Now that the asteroid's size had finally been pinned down and Earth was no longer considered at risk, astronomers turned to a different question, one that initially seemed almost like an afterthought. Where exactly would 2024 YR4 be on December 22, 2032, now that its orbit had been calculated much more accurately? NASA's Center for Near-Earth Object Studies combined Webb's infrared measurements with every available observation from ground-based telescopes and recalculated the asteroid's future trajectory. The improved solution revealed something nobody had expected. Earth was safe. The Moon, however, might not be. Earlier calculations had suggested only about a 1.7% chance of a lunar impact. But once Webb's March observations were included, NASA updated the probability on April 2nd to 3.8%. The story still wasn't finished. On June 3rd, just before 2024, YR4 faded beyond the reach of every telescope capable of tracking it. Webb managed to capture one final observation. It would become the last useful measurement anyone could obtain before the asteroid disappeared into deep space, where it would remain invisible for years. That final observation proved invaluable. It refined the asteroid's predicted position by nearly 20% and pushed the estimated probability of a lunar collision even higher. The new figure reached 4.3%, the highest official value it would ever receive. NASA found itself delivering an unusually strange message. The asteroid no longer posed any meaningful threat to Earth, yet it now carried roughly a 1 in 23 chance of striking the Moon, and there would be no opportunity to collect additional observations for years. Ironically, that possibility unsettled many planetary scientists even more than the earlier Earth scare. Not because the consequences would be greater, they clearly would not, but because of what such an event would represent. An impact on the Moon would never endanger Earth directly, nor would it noticeably alter the Moon's orbit. Compared with the Moon itself, an asteroid the size of 2024 YR4 was insignificant. Still, it would not be meaningless. Far from it. If the asteroid had struck the Moon, the consequences would have reached far beyond a spectacular flash in the night sky. The Moon was no longer the empty, untouched world it had once been. By the early 2030s, multiple nations and private companies planned to place equipment on its surface, particularly around the lunar South Pole, where the next generation of exploration aimed to establish a lasting human presence. A 60-meter asteroid slamming into that environment would have thrown an enormous plume of debris into space. Much of it might have been visible from Earth through nothing more than amateur telescopes. More importantly, any spacecraft, surface hardware, or even astronauts operating near the impact site could have faced genuine danger. Satellites orbiting the Moon, assets becoming increasingly important for future navigation and communication, could also have found themselves in harm's way. Beyond the practical risks, such an impact would have created something humanity had never experienced before. For the first time in recorded history, people would have known the exact date in advance when a sizable asteroid was going to strike another world, and then watched it happen. It would have been an extraordinary scientific event. As public attention followed the story, many headlines reached for one dramatic phrase: "City Killer." It was memorable, it was alarming, but it was never the language NASA officially used. In reality, the phrase often exaggerated the actual level of danger that astronomers had calculated throughout the entire episode. An asteroid measuring somewhere around 60 meters across certainly had the potential to cause devastating local destruction if it happened to strike directly over a heavily populated city. Some estimates compared an impact of that size to the famous Tunguska explosion of 1908, which flattened nearly 2,000 square kilometers of Siberian forest. But those comparisons left out an important piece of the story. The overwhelming majority of Earth's surface is covered by oceans, deserts, forests, mountains, and other sparsely populated regions. The probability of any asteroid this size striking the center of a major city was never part of the impact percentages appearing in headlines. Throughout the entire event, NASA's public statements remained remarkably restrained. Even when the calculated impact probability briefly climbed to 3.1%, the agency repeatedly emphasized that, by far, the most likely outcome remained exactly the same: a clean miss. And that was precisely what happened. Right on schedule, the asteroid quietly vanished from view. Beginning in June of 2025, 2024, YR4 became too distant and too faint for any telescope on Earth, or even in orbit, to continue tracking. Astronomers knew it would eventually return, but not for several years. For almost an entire year, the last official number anyone had was the 4.3% chance of a lunar impact. Meanwhile, the asteroid itself continued its silent journey around the Sun, following an orbit that now existed only inside computer models and mathematical equations. There was no practical way to compare those calculations with fresh observations. Most people assumed that was where the story would pause until the asteroid returned. Instead, an unexpected opportunity appeared. In February of 2026, an international research team led by astronomer Andy Rivkin of the Johns Hopkins Applied Physics Laboratory, together with MIT researcher Julian DeWitt and several collaborators, realized that two brief observing windows might allow the James Webb Space Telescope to detect the asteroid much earlier than anyone had believed possible. The idea depended on another remarkable spacecraft. For more than a decade, Europe's Gaia mission had been measuring the positions of nearly 2 billion stars with astonishing precision, creating one of the most accurate star maps ever assembled. The researchers realized that if Webb could observe 2024 YR4 passing in front of a carefully selected field of Gaia-cataloged stars, those stars could serve as an extraordinarily precise reference grid. Even if the asteroid itself appeared almost invisible, astronomers could still determine its position with exceptional accuracy. It was an elegant solution. On February 18th and again on February 26th, 2026, Webb attempted exactly that observation. The effort succeeded. In fact, it became the faintest confirmed detection of any near-Earth object ever achieved by the James Webb Space Telescope, a remarkable technical accomplishment regardless of what it ultimately revealed about the asteroid's future. When those new measurements were combined with every observation collected since the original discovery in December of 2024, the improvement was dramatic. the uncertainty surrounding the asteroid's future position shrank by roughly a factor of 12. A prediction that had once spread across a significant fraction of the Moon's diameter suddenly narrowed into something vastly more precise. The answer arrived on March 5, 2026. NASA announced that 2024 YR4 would pass approximately 21,200 kilometers from the Moon, with an uncertainty of only about 800 kilometers. The asteroid would miss completely. The lunar impact probability that had briefly climbed to roughly 1 chance in 23 disappeared entirely. With the improved orbit now firmly established, NASA extended its calculations a full century into the future. The conclusion was reassuring. Not only would 2024 YR4 miss the Moon in 2032, but no meaningful risk of an Earth impact appeared anywhere in its predicted orbit over the next 100 years. With the new observations in place, the story that had once seemed frightening finally reached a clear conclusion. NASA's updated calculations placed the official probability of 2024 YR4 striking Earth during its 2032 encounter at roughly 0.0005%, about 1 chance in 20,000. In the language of planetary defense, that number was close enough to zero that the discussion could finally be considered over. The uncertainty that had dominated headlines only months earlier had disappeared. Soon afterward, the international research team published its complete findings in a peer-reviewed paper during July 2026. The publication formally confirmed that the asteroid would safely miss the Moon, while also demonstrating something equally important. Emergency observations with the James Webb Space Telescope had opened an entirely new chapter in planetary defense, proving that they could dramatically improve the precision of asteroid tracking when every kilometer mattered. Even then, the story still had one more surprise waiting. Around the same time, 2 amateur astronomers, Sam Dean and Derek Lamb, began searching through decades-old archival sky survey images. They weren't operating billion-dollar observatories or commanding spacecraft. Instead, they carefully examined publicly available photographs taken years before 2024 YR4 had ever been discovered. Eventually, they found it. Hidden in plain sight, the asteroid appeared quietly in images nobody had paid attention to at the time, because nobody had known it was there. Those forgotten photographs extended the asteroid's observational history by years, giving professional astronomers even more information to refine its orbit. It served as a remarkable reminder that even in an age dominated by automated telescopes and artificial intelligence, patient human observers studying old data can still make meaningful contributions to modern science. By the summer of 2026, the situation had changed completely. 2024 YR4 was no longer considered any kind of threat. Its Torino scale rating had returned to 0. The asteroid would eventually swing back into view as it continued its orbit around the Sun, but neither NASA nor the European Space Agency expected to revisit it with any real urgency. For the public, the story ended quietly, almost anticlimactically. Yet what remained behind proved far more valuable than simply crossing one asteroid off a list. Almost by accident, those 18 months had become the first true real-world stress test of humanity's modern planetary defense system.